seen in previous videos how a new theory can explain some of the unresolved questions in standard quantum physics theory. In this video, we continue our exploration and we'll see how we can resolve two of the biggest mysteries in quantum physics by simply applying the rules of our new theory. These so-called mysteries are the entanglement of particles, also known as the non-local causality syndrome, and the wave-particle duality of light. Let's start with the entanglement of particles. In quantum physics, systems like atoms and subatomic particles can be correlated by way of their quantum states, and these correlations lead to behaviors that seem very strange from our usual point of view at the space-time level. An example is two electrons in a collective quantum state in which their spins must always end up pointing in opposite directions, one electron up and the other down. These correlations seem to involve an influence that connects the electrons, no matter how far apart they are. We could think that their individual final opposite states were decided before the electrons were split, but Nobel Prize laureates Aspect, Clauser, and Zeilinger experimentally proved it was impossible using John Bell's theorem. Another possibility could have been that once one electron picked a final spin status, it sent a message to its entangled counterpart. But again, this was proven wrong by many other experiments. All of this seems paradoxical, but it can be understood when we keep in mind that the electrons are actually elements in the quantum substratum, which has no defined spatial or temporal separation, and thus no defined time order. So these influences are not like faster-than-light signals, and they don't violate relativity. What happens is that when the electron spins are measured using photon absorptions, the result is a collapse to a particular value, either up or down. But this collapse is not limited to one electron, since at the quantum level, both electrons were parts of one global system. This means that each electron underwent a collapse to the value demanded by their overall quantum state. Since collapse is really the creation of a new space-time event, the quantum correlation between the electrons affects both events in a correlated way, and we find one electron up and the other down, even though they may be so far apart that no light signal could directly connect them. Okay, it is now time to have a look at the infamous wave-particle duality of light and of quantum particles in general. All entities in the quantum substratum are fundamentally wave-like, in that, in general, they are not strictly localized, and their behavior can be described by a wave equation. It is only upon the discontinuous emission and absorption of photons that these systems become localized, and that is where their particle-like behavior shows up. We can see this in the contrast between the continuous processes in the quantum substratum and the discrete pixel-like phenomena that constitute space-time. So we can, under certain conditions, simplify and approximate electromagnetic transactions by replacing the actual field transactions with small particle transactions, which is what we do in these series of videos. But the reality is that even when we do that, we have to remember that these particles are not little balls moving in the space-time domain. For example, we see a spot on a phosphorescent plate when an electron hits the plate, and it looks like a little ball is leaving a trail on a screen. But what actually happens is that the electron emits waves towards all potential receiving atoms, which in turn emit confirmation waves, and their combinations create probabilities which are used to select the atom in the screen that will receive the energy from the electron. And all of this occurred in the quantum substratum. The reception of the photon in the selected screen atom triggers a complex of phenomena created by chemical changes in the atoms in the screen, allowing us to see a spot on that screen at the space-time level. So, the electron was never a little particle, but it can leave behind discrete traces in the space-time domain, while interacting with other quantum systems in the quantum substratum using wave-like properties during energy transfers. The coming videos will show how to derive general relativity laws from the new quantum rules we've seen so far. It's going to be very exciting, so stay tuned.